Okay, thanks. So yeah, I want to continue where I stopped last Monday. So yeah, so last week I talked about the classical sense theory, and I mentioned that actually we can generalize to the geometry setup. And I think I already. Let me recall what we did. So, so classical sense theory starts with a p-adic field inside QP bar, not necessarily p-adic field. You can take a finite extension of QP or a ramified extension of QP. Here we just consider a rigid analytic space. Let me just put this here. Just rigid analytic variety. And here we can consider Galois representation. And here we can consider pro-eta local system. On X. And recall that, so in sense theory, we studied the semi-linear representation of GK, which is the tensor product V with CP, and consider semi-linear action of GK. And here we just tensor the pro-eta structure sheaf. So this is the completed pro-eta structure sheaf. And this defines a pro-eta vector bundle on SWA K. Here, this just defines a vector bundle on the pro-eta side. And actually, so sense construction. So in the case of K, so it actually also works for any pro-eta vector bundle. So, or concretely, it just means any semi-linear Galois representation. And here, you can also generalize just to vector bundle, not necessarily coming from this form. And I would just probably use this blackboard. So here you have a Sen operator. And here, maybe it's better to emphasize it's really defined for this pro-eta vector bundle. So what you get is not just not just one operator. So actually, you get the D operators, where D is the dimension. So and to make this coordinate free, the best way to phrase this is to write it as a Higgs field. Meaning that first is OX set linear, and secondly, value with itself is equal to 0. So because this has dimension D, so you should think you have D operators, and that's because if you remember in the construction of the Sen operator, so we first almost descend to K infinity, which is K adjoining all the p power roots of unity, and that's a Galois extension of K, which is an open subgroup of ZP cross. This is one-dimensional p-adic Lie group. So essentially this sum operator comes from the derivative of the CP of the Lie ultra, and here you consider the so there's no canonical choice anymore, but once you fix the chart in the sense that you fix some atomic map to the torus, d-dimensional torus, you can look at this this perfectory extension. And here you see the Galois group is the dp1 to the d, which is d-dimensional, so that's why it gives you d operators. Okay, and okay, I think this is pretty much where we stopped last time. So already, okay, maybe I will use this blackboard. So there's one thing I probably didn't quite emphasize last time is that so what's the meaning of sum operator being 0? So here, it's the same as, well, classically this is called Couch-Saitoff with like a CP admissible, which just means that if you look at the GK invariance in tensor back CP, then you just get back V tensor CP. Okay, well, another way to say this is that so this is like you're taking some kind of you're looking at the H0 of this pro-état vector bundle, and when you pull back, you just get back the. So in some sense, this vector bundle descends to spa CP, spa K, sorry. And I should really say this is really pro-état vector bundle. I apologize, I forgot to put that. And here is the same thing. So so this geometric sum operator equals 0 just means that actually this W descends to analytic side or état side. So maybe I will just write in this way. So so where mu is just the push pull of from the pro-état side to just, well, I guess I can also put état side, but you can also just put the analytic side. Okay. So it just tells you when a pro-état vector bundle really comes from the usual état side. And also, you can use this to compute the Galois cohomology. So here, I mentioned last time, so V tensor CP, and tensor back with CP is actually just computed by this two-term complex. Sorry, I have to never start from the beginning. And here, you can do exactly the same thing on geometry, but it won't just given by this two-term complex, but you need to replace this by the Higgs complex. I don't know what's the usual notation, but let me just use Higgs W. Which is just start with W, and you just keep applying this Higgs view. I mean, you batch. It has a length d plus 1, where d is the dimension. And then you have a similar thing. So if you just push forward, from pro-état side to the analytic side, this is, and you put it back. Sorry. You look at the high direct image, and you just put it back, and then you just get the HI of this complex. Okay.
Excuse me. So maybe this was discussed last time, but like superficially, this looks a little bit like a connection on W.
It's not quite connection. It's OX linear.
Oh, I see. Okay. Never mind that. Okay. Also, how are you defining HI? How are you defining HI of like the sun map on the left?
This one or this one?
Yeah, the right.
This one. I mean, this is just a complex, and I just take its HI.
Is it 0 to 1 or minus 1 to 0?
Yeah, 0 to 1.
So sorry if is it also correct that this will work for perfect complexes? Is that right?
Yeah.
And is the last statement then? So is it true that if you write down this Higgs complex as a perfect complex on the pro-étal site, then that has a canonical descent to the étal site, and then this is sort of a statement.
I'm not sure the complex itself. So sorry, you're asking if I replace W by a perfect complex, and
I mean, if you fix W and you take the Higgs complex, that's a perfect complex.
Yes.
And then that's on the pro-étal site. Does that sort of naturally descend to the étal site such that you get this?
That's something I'm always confused, so I don't want to claim it. And I'm sure when you... Yeah, that's something I don't know. Yeah. But you think it's correct?
Well, it just seemed like when you do this, then you're sort of, when you form the Higgs complex, it seemed like you were making the data 0.
Yes.
If you did descent.
Yes. Okay. Sorry. I felt I made some mistakes in the past once, and then I tried to avoid this problem. But yeah, sorry. I don't know. Okay. Maybe any other question? Yeah, so for me, I would just say for me, this is already good enough for a lot of purpose, because we will see most applications actually, we will just compute this complex and it will just concentrate it in 1 degree, and this is already enough for most of my application. Okay, and also I think I mentioned last time that Sen later generalized this to some infinite dimensional setup, and as a consequence is that, so if you just say you have a Galois extension, which is a G, which has Galois group G, which is a p-adic Lie group. Then you can define that, you can define the Sen operator in some sense for this extension, which is just Lie G CP. Okay. For example, you can just consider all the locally analytic function on G and just do this. And here you can consider the same thing. So if X, let's say I have some pro-état cover, let's say with pro-état G cover, and you just get a Higgs field with value in the Lie algebra. So this means that This notation just means that I view the usual joint action of G on it I view as a local system, okay, or view as a pro-état local system, and so this gives me an element there. Okay. Almost the same thing, except I just need to tensor this cotangent bundle. Okay, now I don't want to talk about the actual definition, but I would just say basically you just you construct it from this. But as usual, so you don't really don't calculate things using the definition. So we need some other way to compute this. So I would say, yeah, let's. So what's the main example we want to study? So it's the following. So let's say X. Now I'm slightly abusing notation. So let's say I have X is some region analytic variety, and I have an elliptic curve over. Maybe that's the main example we want to study. So some elliptic curve over X. So from this, I can just trivialize this p-adic état p-adic Tate module, or dually, I just trivialize the H1. So I can just look at and p squared. And then this, let me denote this by x theta, and this just defines a pro-état tensor with GL to ZP. So this is a GL to ZP tensor. And the natural question you can ask is, what is this element? Okay. Just in this simple case. Of course, at the end, we want to just apply it to the universal case. It's just you take X to be a modular curve, and you take this to be a universal elliptic curve. And also, I apologize that so I will ignore compactification. So there's a Kummer, there's a logarithmic version of everything I talk about, and so when I actually want to apply it, I will apply the Kummer version. So this I can take X even to be the compact modular curve. But I will just ignore this in my talk. Okay, so
Sorry, can I just ask one clarification question? So this theta x tilde, I think you explained it last time, but is it a consequence of the theta for vector bundles? Is that
not for vector bundle. You need some infinite dimensional version of that. Yes, that's a good. So you really want to consider V to be all the locally analytic functions on G, which is infinite dimensional, and then you get the Sen operator, and you can show it really comes from an element in the Lie ultra. But yeah, itself doesn't quite follow from the finite dimensional version. Yeah. Here is the same. You have example. Yeah. Any other question?
Conversely, if you have a Galois representation which comes from a representation of G, you can describe the Sen operator in terms.
Yeah. Yes. Yeah. That's also another way to. Yeah. So you were saying probably you just need the finite dimensional version.
No. Just saying that maybe you can also go backwards.
Yes.
This, if you compute this one, you get some consequences.
Yeah. So this, I think the comment here is that if you have a G representation, and let's say you have a map from homomorphism from G to some GLN, then if you get an n-dimensional representation and you get the Sen operator there, but actually it just agrees with mapping this universal Sen operator to that GLN. So that's why it's sort of enough to calculate this element so that for any G representation, you know what Sen operator is. Yeah, so this is basically the example we want to study, and so actually, in practice, our situation is a lot better in the sense that actually this is not just defined over CP, but actually this is even defined over QP. But actually everything is even defined. Well, let me just write K. So K is a finite extension of QP. Okay, in this case, actually, you're better than just over CP because if let my L over be this rank 2 local system coming from the relative H1. Actually, this is a de Rham local system. Meaning that it's associated to a variation of Hodge structure. Okay, and so the point is that so we can try to use variation of Hodge structure to actually compute this element. So that's why I say it's we are better than just giving ourselves something over CP. We can really try to just make use of this symmetry over because it's defined over K. So I would just so the rest of so it's not. I don't really have to restrict myself to this situation of like coming from elliptic curve. I can just start with a de Rham local system and try to explain. I will explain how to calculate the what is the geometric operator. So that's the and not surprising. So if you want to okay. So this is closely related to the p-adic Simpson correspondence. P-adic Simpson. So I will just start with this data, so x over k, and I'll have a de Rham local system. So just want to fix some notation. So x over k. So k is as before, and L over x is a de Rham local system. Meaning that it's associated with so D, which is a vector bundle equipped with a Hodge filtration plus a flat connection that satisfies Griffith's transversality. Okay, so let me just remind. So D is a vector bundle on X, and number is a connection. And this Hodge filtration satisfies Griffith's transversality. Hodge filtration. So number of a field I is in the field I minus 1. Okay, and so de Rham local system just means that you can find, actually it will be uniquely determined by this L such that when L tensor the OB de Rham this de Rham period ring on the pro-état site is isomorphic to D tensor OB de Rham. And compatible with filtration and a connection. So there's connection on natural connection and the filtration on OB de Rham, but there's no such thing on L. So you just consider the connection and filtration here, and here you take the the product one. Okay, so that's the meaning of the wrong local system. Of course, there's a very simple, there's a nice criterion. You just need to check at a point, but that's what we are going to use. So the very vague idea is as follows. So if you start with the Drum local system, then so this construction just gives you variation of Hall structure, which I mean just this data. So from L, get to this D. And from variation of Hall structure, there's a very standard construction to get the Higgs field. Basically, you just do the following. So Higgs field. So a Higgs bundle. Basically, you just look at D. Sorry, I should be more precise. On X base change to CP. And so you basically do this. You tensor this with B de Rham. So the absolute de Rham, the usual de Rham period ring, and it has a natural filtration, the p-adic filtration. Okay, and maybe you even I don't think you really need. You need to take some completed tensor product, and you just take the graded zero's graded piece, and that actually will give you a vector bundle with the same rank on XCP. And if you take the graded zero piece of the number, then you just get a Higgs field. Okay, so concretely, this one is nothing but you take the arc sum of ger I of D, then base change and then tensor with the CP, maybe with minus I, if I'm correct. Okay. And you, and you when you take the graded piece of this connection, because of this Griffith's transversality, actually it's OX linear. So it just actually the Higgs field you get is just sending this to I minus 1D tensor omega 1. So it's just I of Nabla. And so the Higgs field here is you just take the dark sum of I with maybe take twist by minus I. It's not quite dark. So I really mean from I's graded piece to I minus 1's graded piece. But I hope it's not a too bad notation. Okay, so this is just a very classical construction. And here, so we have already discussed from a local system, I just get a vector bundle or Higgs vector bundle on the pro-état side. Actually, it's, okay. So the point is that actually in here, so this is just L to L tensor OX hat, and it's equipped with a Higgs field. And the point is that actually, instead of going directly from L to this, but actually we can first go to this. Okay, this might lose some information, but actually, and then we pass here, and then we can recover this from this data. Okay, and very vaguely speaking, so this is there's even some bijection here. If I'm maybe even let me just put the projective even proper here, and after some choices, so there's even bijection, and this is what I don't know. Some people nowadays call the p-adic Simpson correspondence. Which was in the curve case first even proposed and proved by Faltings and in general by Benhuai. Okay, so that's a rough idea how we actually calculate the geometric operator or the Higgs field here. So we will really try to extract it from this data. But this is just very vague, so now I'm going to state everything more carefully. But before doing that, are there questions? Yeah.
You need the Durham assumption to, like, suppose you set any local system, like without the Durham assumption, would like you'd still have the horizontal error and the downwards error from L, right? But
no, I don't have horizontal. Horizontal one's only for the Durham local system. That's the definition.
Oh, okay.
Yeah. Any other questions? Okay, so yeah, this. Okay, so so if you start with Durham local system, so it has a so-called Hall-shaped filtration. So it is an increasing filtration. So and the definition is as follows. So minus I x hat. It's m. I will explain the notation after m0 modulo tm intersect with ti m0. Where so m is a B Durham plus local system, which is given by L tensor B Durham plus. Okay, so this is the bold B Durham plus, not the absolute one. Okay, and we know that if we invert T, that's just by Durham assumption, that's just equal to D tensor OB Durham. But inside of D tensor OB Durham, I can also get a lattice just by, without inverting T for OB Durham. So M0 is just defined as D tensor OB Durham plus, and then you take a nabla equal to 0. Okay, so both after you invert T, this is just L tensor B Durham, which is the same as D tensor OB Durham, and then you take a number equal to 0. So there are two lattices inside the same, and just by measuring the relative position, you just get a. I forgot to say, so this is like a GERD 0 of this. So just by measuring the relative position, you just get a filtration, natural filtration on it.
Sorry, just to say that the right-hand column has become an inclusion, but not equals once you put number.
This one?
All the way to the right?
This is inclusion?
No. The vertical, all the way to the right?
Right.
That equals is maybe not equals once you put number.
That's equal?
Oh, sorry, it's B Durham upstairs, not OB Durham. I got confused.
Yeah, that's okay. And once you have this, if you just and it actually follows from this construction that if you take the grade A piece of your Hall-shaped filtration, this is just naturally isomorphic to ith graded piece of D with some Tate twist. And so here's some quick facts. So we have this Higgs field on L tensor or exact, and now I have a filtration, and simply because of functoriality of the Higgs, this Higgs field, so it must preserve the filtration. Well, secondly, so when you look at so it also acts on the graded piece, but each graded piece is really an analytic vector bundle. It's just a pullback of an analytic vector bundle, and I think it's still there. Then the same operator is 0 here, which just means that actually it sends field I to I minus 1. Okay, it's just because yeah, sorry, it's here. The graded piece is a top vector bundle. So in particular, it's nilpotent. Actually, this is a general feature if it comes from, well, I think essentially I give a proof that this comes from de Rham. Okay, and the last statement, I just calculate this because now it induces a map from GER I to GER I minus 1. And so let me give a name. I think I wrote, yes, let me remind you, this is what I call W. So GER I W, when you look at the, when you apply the Higgs field, you get a map to GER I minus 1. So omega 1 minus 1. But this, from this factor that this is just isomorphic to ID 0 with Tate twist by I. Okay, and this is just isomorphic to GER I minus 1 D by. So at first I have I minus 1, but there's also another. Wait, no, I'm confused. I think I messed up some numbering here. There should be probably some minus I here. Okay, I think I apologize. I think at the end this number should be the same, but it seems the only way to make it the same is to change this I to minus I. So yeah, I apologize. So I don't quite remember it. Yeah, I will check it and correct. And correct myself later tomorrow. So if this is correct, then this should be minus I. And so the point is that this commutes. So this is just the gradient map of my connection. Oh, sorry, this is so let me go on. And this is just the gradient map of my Higgs field, and the point is that they agree, or up to a sign. So it really depends on what's your convention for this. So I'm not really going to prove this for you, but but I just want to say actually the key calculation is you don't really need. Actually, it has nothing de Rham with the de Rham local system. You just need to compute to calculate this Higgs field for so-called OC, where so OC is defined as square zero of OB de Rham. Okay, so some infinite dimensional polytopic vector bundle. So it's not too bad. Actually, it's just it can be written as a union of finite dimensional polytopic vector bundle. So the point is that so here you have a Higgs field, this canonical Higgs field. On the other hand, so simply because it's a GERD zero of OB de Rham, so it also has a you take the graded GERD zero of the connection, it goes to OC tensor omega 1. And some of the point is really to calculate this on this OC, and you will find it's just up to a sign really just agrees with this. So the point is that you just need to calculate everything just in this universal case, and then what I just stated here, it just follows from this.
Yeah. So I mean, in this analogy with like de Rham mod p-de Rham cohomology, there's this Katz condition of two things agreeing, and is that a little bit analogous to this?
You mean this one?
Yeah, these two things agree.
I would guess so. Yeah, but I thought you or people in the audience definitely know much better than. Yeah. Any other question? Okay, so if you believe me, then we will just assume this and see how to answer this this question here. So in the case of elliptic curve, so everything is much simpler because the Hodge filtration is you only have field one. So okay, let me just write down. So and this so back to elliptic curves. Okay, so we have this L, which is let me just repeat what I wrote there. So I have the rank 2 local system, and so then you have the variation of Hodge structure. In this case, it's nothing but the relative de Rham cohomology. And equipped with the Hodge filtration and also the Gauss-Manin connection. Okay, and in this case, the Hodge well, in this case, this GERD of not, but it's simply what people usually call the Codera-Spencer map. So if you start with field 1 of, let me call it D, you apply connection, just D to omega 1, and then you just project to GERD 0. And so this map, the composite of this map is just let me denote by KS, which stands for Codera-Spencer. I'm sorry. Usually the field 1 well, as usual, just the relative cotangent bundle. So this sometimes I would just simply denote it by omega or omega 1. So then this result basically tells you that this Higgs field, this theta W you want to compute is graded after you take you consider Hodge-Tate filtration and look at the graded map is essentially given by the Caldera-Spencer map. Okay, so let me just rephrase this result. So let me remind you, so we want to calculate this element. So where does it live? So it lives in the Lie algebra of GL to ZP tensor OX hat tensor omega 1, right? But this Lie algebra is nothing but just well, we all know this is just a home of L to L. Okay, so I would just try to calculate the element inside home L to L tensor OX hat and tensor omega 1 minus 1. Okay, so I will just write here. Okay, so let me repeat what these factors using this language. If you find this too abstract, I hope this is better. So here,
Can you move the backboard up? Oh no! Sorry, could you just move the backboard up? Sorry.
Oh,
Yeah, so we can see.
yes. Is this better?
Yes.
Thank you. So, okay, let me write this down. So I forgot to say, so this L tensor OX hat, so this has the Hodge-Tate filtration. So the Hodge-Tate filtration, basically now this becomes the quotient. So this is Q1B. And it has this GERD 0 as a sub, and there's a Tate twist, and now I'm not very confident about all my twists here. But yeah, if I trust what I wrote there, this should be -1, but what? Yeah, I couldn't. I think this really should be -1.
It was a little better.
What?
For cohomology, -1 looks better.
Yes. So that's okay. That confirms that should be -I. Okay, so this is the Hodge-Tate filtration. So this is W. Then this is just field 0W. Okay, and this is just GERD 1. Okay, so we want to calculate this universal Higgs field, or canonical Higgs field, which is out OX hat, so omega 1. Okay, so I can just first rewrite this as I'm taking the home of this vector bundle. So just move OX hat inside. This is the OX hat linear. Okay, and now the fact, I didn't number them, but the first just says that actually it lies in the subspace preserving the filtration, the Hodge-state filtration. I will just write W. Then the next is a nilpotent. Well, because it's nilpotent, it just means it's 0 here, and essentially induces a map from this curve 1W to field 0W. So this means it's in home, or it's out from curve 1W to field 0W. Answer omega 1 minus 1. Okay, just because it's nilpotent. But this, we just unravel everything, so this is just so I already write here, so curve 1 is just omega. And this is field 0 is just this curve 0. 0D, for 0D, and tensor omega 1. Okay. And all this, and this diagram basically just says that, well, this element is just the same as the Cordero-Spencer class inside of this home. That's basically what this result really says in the case of elliptic curve. So in short, at the end, you just recover the Cordero-Spencer class, which I think it's not quite in this language, but it's like this was Fontaine did some calculation first, which I think essentially equivalent to this. In his paper, determined the Hodge-shaped base for modular forms, for Galois representations attached to modular forms. Other questions so far? So next I want to rewrite this result in a more group theoretic way when we are actually over the modular curve. Yeah.
So it seems like you have like a bunch of containers on the home. So why does the Cézanne operator lives inside the home OX, like the most bottom part?
Lives
like in the most bottom part, because it seems like you're just doing a bunch of containment.
We just argued by the potency of
So this one is as I say, it's nilpotent. So it will be 0 here.
Ah, okay.
So it induces a map from here to here. So that's why it's in this home.
I see. Thanks.
Yeah.
I have a question. Like in your paper, and also what Fontaine did is kind of computing some like Grail 1 and doing some very explicit computation of the cell operator. Probably this is not contained here. This is verifying this is the same as Fontaine's extension, but how do we understand the explicit computation via Fontaine's extension?
Well, that's what I didn't explain here. So GERD 0 OB Durham is closely related to Fontaine's extension. It's basically symmetric power of Fontaine's extension modulo some ideal. So that's why if you understand what's this kind of the cell operator, geometry cell operator on Fontaine's extension, you also under this one. So that's why essentially it's a calculation about Fontaine's extension. Any other questions? Okay. Now where did I start? Okay. Now let me specialize to the case of modular curve, because in that case, actually, the Cordero-Spencer is actually an isomorphism. No. X is so modular curve let's say of the level for pk lower p. Sorry, I want to take full level at p. Okay, and this, as I say, I will ignore props. So you can also just pretend I'm considering. So I will just consider the compact modular curve. Okay, and so in this case, I have x. And this x theta is nothing but so the so-called modular curve with infinite level at p. So it's just the inverse limits of x k over p, k lower p. Okay, so because it's basically the definition, so you just trivialize the Tate module, the H1 of the universal elliptic curve at p. So on this x theta, so L is canonically trivialized. So that means that if you look at the Hodge-Tate filtration, so you just get the trivial vector bundle, and this Hodge-Tate filtration just gives you a sublime bundle. So the position of omega, not omega, phi 0. W inside L tensor x hat. Defines a map, which first discovered by Schulze, called the Hodge-Tate period map from x theta to to the flag variety, but in this case, so the flag variety, but in this case, it's really just P1. Okay, it's called Hodge-Tate period map. From here, I get a map to the flag variety. Okay, and let me just remind you. So P1 is really, or the flag variety is really just a G mod B, where G will be GL2 and B is just the usual Borel. And the modular interpretation of the flag variety is that it parametrizes Borel sub. I will use the Lie algebra version. So Borel sub Lie algebra, Borel sub algebra of GL2. And also we know that so from this description, so if I have a B representation, then I just get a G equivalent vector bundle on G mod B. So if I have a representation of B, there's a natural functor from this to the vector bundle on the flag variety. It's G equivalent. Actually, I don't quite need this. Sorry, I still need to introduce some notation. So this is my GL2, and I've fixed the standard Borel sub-algebra. And also I use N to denote its unipotent radical. So concretely, this is this, and this is this. Okay, and of course B just acts by the usual joint representation. So if you just, for example, you start with the GL2, then you just get actually the trivial vector bundle let me denote by G0. Actually, I learned all this notation from the paper of Billings and Bernstein on localization, which is so this is so. 2. And if you start B, you just get a subvector bundle. So concretely, using this description, you're just looking at all the sections such that at each point it lives in the corresponding parallel. So just so at each point there's P1. It gives you a parallel, and also let me use an X to denote this unipotent radical. So this I just ask at each point it lives really in this in the corresponding parallel, and N just corresponds to its Fx inside the Nx. Okay. And the nice thing is that from using this picture, this Hodge-Taylor period map, I can just pull back this vector bundle to the infinite level modular curve, and now I can just rewrite what I have here. So this is nothing but this is just whole. If you remember, this is just a GL2, the Lie algebra. So this is just a pullback of G0. And this preserves filtration.
Some omega 1 or something?
What? Yeah, sorry. Is that what you're asking? Yeah, thank you. Yeah, sorry. Yeah, I want to say this is really the pullback. And this preserves filtration. Well, exactly just means that it's inside the corresponding, the pullback of the Borel. And this nilpotent just means that this is actually in the pullback of N now. Okay. And now, okay, I will just, now in the case of modular curve, it basically follows from, I don't know, I don't want to, the general theory of like a modular alpha of n variety, or in this concrete case, you can just prove everything by hand, is that, the fact is that this Caudaire tensor is an isomorphism in the case of modular curve. Okay, what does it mean for us? Well, first we know Caudaire tensor is a class here, so this is really just a line bundle. So it just means that it's actually a generator of this element. So corollary. So zeta stuta here in the H0, it's stuta actually, it can be improved, but let me just first write in this way: 0 tensor omega 1 x is a generator. Okay. So this is very nice in the sense that actually, so this zeta x theta in general is very hard to describe, but now we actually have a purely group theoretic way to do this, because this just comes from a pullback from elements from the flat variety along Hodge-Shape period map. So in some sense, all the calculation if you want to do now, you can just try to do on the flat variety and then try to pull back.
The definition for is it h0 over x tilde, not x?
Well, it's also, it descends to x, but also you can pull back to.
I think the formula upstairs take the whole section.
But the formula there is on x. Yeah, sorry. Yeah, okay. Yeah, I apologize. So this equality really means I pull back this to x tilde, then you get this equality, yes.
So just to clarify, you're saying that theta x tilde is something that lives over x, but the formula that you're explaining is that after you pull back to x tilde. Is that right?
Yes. Another way to say this is actually OGL2 ZP equivalence. Yeah. So
After pullback, it's a section of.
yes, it's a section. Yeah, or GL2 ZP invariant section. I mean, that's basically what's. Yeah, I apologize. Maybe if I'm using this, it's better to do this. Yes, thank you. Any other questions?
So the -1 on the like the -1 twist.
Yes.
This only matters somehow for thinking about this GL2 ZP action.
Yes. We will see. Actually, it has some meaning, but not at the moment.
But in sometimes right now, this is roughly like some omega, like O twisted by 2 times O twisted by -2.
Yeah. Yes.
Equal to O.
Yeah, exactly. Yes. Any other question? Okay, so let me just remind you how to why we care about this as a well, probably we'll talk about this tomorrow. But so the second corollary is that so if you remember, so if I have a pro-état local system, then I can try to use this to help me compute this push forward to the état side. So in this case, if I consider all the locally analytic functions on GL to ZP, so I would just simply write as a CLA, which defines a pro-état local system on X. Tensor with OX hat. And I want to compute is pushed forward to the état side. And if you remember, so I can just calculate this. Well, after pulling back sorry, I will just write here. After you pull back to pro-état side, it's really, this looks, I can just calculate by the two-term complex here. Theta. Tensor omega 1. Okay. And actually, as I say, so this is just a constant thing. So you can just do the calculation on the flat variety and then use Hodge-Shape period map to pull back to the infinite level modular curve and calculate this. So very roughly speaking, what you get is that this lives in degree 0. Okay, but by some not too hard computation, it's pretty much the same as in the work of Berger Comets. And if you look at what does it mean on the left-hand side, so this locally, you're basically calculating, so this, so I sort of want to say that this is more or less calculating OX theta. So this is structure sheaf on the infinite level modular curve, and you take its locally analytic vector. So you just you take this GL2 ZP locally analytic vector, And so what's on the right-hand side tells me that there's no higher locally analytic vector. So that means it's actually very nice. When I just calculate, take the the subspace of locally analytic vectors, actually, that's it. There's no higher HI. So this is no higher LA. And moreover, so I then get a description of the locally analytic vector after I sort of pull back to OX theta. So I guess, yeah, maybe I should just use a new blackboard. So I'm slightly abused of notation. So x theta. So now I just view it as in this case, it's just a perfectoid space to x. Okay, so let me just call it. So it's a perfectoid space. And then maybe let me call this pi GL to GP. So what this really tells me is that if if I'm looking at the locally analytic vectors, maybe it's just a bit more. Let me be more precise. Okay, and I take the locally analytic vectors, and then the pullback I will just in some sense tensor with the structure sheaf of OX theta. Okay, and that's just the same as the right-hand side, which is just the kernel of this theta x theta, but theta x theta is just a generator of this n naught. So it's just have to move it to locally analytic functions on GL2GP with OX theta coefficient, and then q'd by this n0. Okay. So this is over OX. Okay. So roughly speaking, so this you should think that it really looks like the locally analytic functions on this p-adic Lie group with OX theta coefficient, but annihilated by a differential operator. Okay. So in particular. This one is annihilated by this n0. Okay. How much time do I have? I have probably 10 minutes. Okay. Okay, so once I have this, so then if you're familiar with localization, you sort of know what you can do next. So this I would just use this as a. So this you should really think. Well, I think I already wrote there. So it's OX theta. At least if you put back. So okay, maybe let me define this here. So let me denote this. Use this notation OX theta LA, which is the subsheaf of OX theta given by taking GL2ZP locally analytic vectors. Okay, so each compact open. Here is fixed by an open subgroup of GL2ZP, and you can take the locally analytic vectors with respect to that open subgroup, and it really doesn't depend on that choice. So this makes sense, and it's easy to see it's a sheaf.
So what's the relationship between that guy and the push forward?
This guy and this guy. So very good question. So if you just pull back as a sheaf to x tilde, and then you take the direct limit over all the level at P, then you just recover this guy. Yeah, so so from this to here, you still need to do one more step. Yeah, just to take the limit, the direct limit over all the level. Yeah. Yeah, so maybe, yeah, it's better to write down. So this is xkp, xap. So this is just equal to, let me call this pi k lower p. So this is just pi k p. Sorry. Okay, I prefer not because I don't have time. But I will come back to this next time. So as a consequence of this, so we know that so we get an action of H0 of B naught mod N naught. I mean, a priori the B naught acts on it, but since N naught is 0, so I get an action of this quotient here. And this actually, if you think about pointwise, it just gives you a Cartan quotient. So actually, this is just isomorphic to a Cartan. So, for example, because I already fixed the Borel, it just you can just identify with this diagonal matrices. So I just got this Cartan action, and the last result just yeah, if you remember, so the motivation I talked about the last Monday, I say I want to tell you some relationship between the hot-shaped weights and the infinitesimal character. So in short, both will all be provided by this H action. So that will be the last result. So theorem is that this action this OLA x tilde on the one hand, so this is related to infinitesimal character of GL2QP, meaning more precisely, so if I look at the center of the universal Lue-Pan algebra, and by Hertzsprung, this is isomorphic to symmetric function on H, the W invariance. And so here, I need to tell you my normalization, so I will choose that, so this is the center at rho. The half sum of a positive root. Well, there's only one now. So just take half of it. Okay, and so because everything, well, I take the locally analytic vectors. So there's the Lie algebra GL to acts on it, and so it acts on OL AX tilde. But here it's a W invariant of SH. So from the H action. I get a SH action, and the point is that this diagram commutes. So in some sense, this H action enlarge the action of the infinitesimal character. So this is essentially just another way to rephrase Hertzsprung isomorphism. Okay, so that's why I say it's related to infinitesimal character of GL2QP, and on the other hand, it's related to infinitesimal character of the Galois group GQP, which is not quite defined, but really what I mean is the Sen operator. I mean the arithmetic Sen operator. So so this, if you fix a causative compact open subset on X tutor, it will fix by GK, where K is a finite extension of 2P, and so it's a semi-linear GK representation. And yeah, I apologize, I didn't quite talk about this, but actually for this semi-linear, you can verify actually it's continuous, and so that sense results still apply in this case. So you get a Sen operator on it. So let me denote by this. This is the Sen operator from the GQP action. And the point is that so if you look at this result, so already you have the infinitesimal the center of the universal Lue algebra act on it. So in some sense of passing this to SH, you just it means that you get some extra symmetry, and this extra symmetry exactly comes from this Sen operator. So more precisely, so if I look at if I identify with this diagonal H with diagonal element, so this element, I say this element agrees with zeta Sen on OLAX tutor. Okay, and you might ask, so where does this element really come from? So in general, actually, all I talk about today, really, you can make sense on general Schema variety. And this really element really comes from Hodge co-character up to a sign. So just a remark. This comes from. And in a more down-to-earth term, I guess I already erased it. If you remember, I have when I identify the graded piece of Hodge filtration and the graded piece of Hodge-Tate filtration, there's some Tate twist, and that's exactly explained by this here. Yeah.
This is reminiscent of the Grothendieck-Springer resolution, where you have, something which lives over the flag variety and also lives over the Lie algebra, and then the action at the Harish-Chandra center extends to an action of as symmetric algebra of the Cartan.
Yes.
Is that how I should think about this picture?
I don't know. No. Yeah. I could only understand things in a very probably elementary way. Sorry. Yeah, I probably don't have time to give you the proof, but yeah, the proof is basically just what I said. So it really comes from the Hodge-Tate filtration. You want to compare Hodge-Tate filtration and Hodge filtration, and that will give you this. And so yeah, that's all I want to say today. So yeah, I was told to give another talk tomorrow, and hopefully I can explain some application of this result next time. So yeah.
Because of short of time, so any quick questions?